Okay, so hello and welcome again. So this is the second mini course on invariant theory of Hamiltonian mechanics and related numerical analysis. So we have Oscar Cosserat, probably it's right. I am not sure the last name. He is a postdoctoral fellow at the Göttingen University and he completed his PhD from the University of La Rochelle, France. And he mostly works on theoretical mechanics, numerical analysis, and differential geometry. So today he will be talking about Poisson manifold and Hamiltonian system. And yeah, over to you, Oscar.
Yeah, thank you. Hello, everyone. So this lecture is titled Invariant Theory of Hamiltonian Mechanics and Related Numerical Analysis because I will explain how one may use geometrical tools to construct numerical methods that are appropriate to approximate Hamiltonian dynamics. So I will explain all these words. We will see what the Hamiltonian system is today. And well, the aim of the lecture of today is mainly to explain the basic concepts of the lectures, what is a Poisson manifold, what is a Hamiltonian system, and also why traditional methods cannot are not appropriate for the numerical simulation of Hamiltonian systems in the framework of Poisson geometry. So first, let us start with a bit of science history. Probably the history of let us start the history of mathematical physics with Isaac Newton. So Isaac Newton published an important book in 1687 where he wrote the second law of Newton, now what is called the second law of Newton, which states that the forces equals the mass times the acceleration. And after him, many researchers in mechanics and physicists and mathematicians, geometers, used this second law to model the universe through dynamical systems and deduce some invariant theory of such dynamical systems. So what happens after Newton is that Émilie du Châtelet translated the book of Isaac Newton from Latin to French. That was at the beginning of the 18th century, or the first part of 18th century. She also commented this book, so the translated version is commented in French as well. She added some comments to Newton's work. And then Lagrange and also Laplace, that was his colleague at Académie des Sciences in Paris, used the second law of Newton to investigate some celestial mechanics, and there were they've been applying the second law of Newton with much success to explain the orbit of planets in the solar system, but they were missing some tools. And one of the tools they were missing was the Poisson brackets that has been introduced by Simeon Denis Poisson in 1808 in Paris during a talk. So Simeon Denis Poisson was 25 years old, I think, when he introduced the Poisson bracket. About 20 years old. And this stimulated a lot Lagrange and other mechanics researchers in Paris. And they could keep on investigate celestial mechanics using these Poisson brackets. And then the story goes on. So Jacobi, in what is now Germany, it was Prussia in the 19th century, kept on investigate the geometric properties of this Poisson bracket. So Jacobi is the one of the Jacobi identity, or Jacobi identity, of the Lie algebra. So, for instance, Jacobi discovered a famous equation in 1842. Oops, sorry. Which is now called Hamilton-Jacobi equation. We will talk about this later on. And Hamilton in Ireland gave his name to Hamiltonian systems. So those are dynamical systems related to the second law of Newton. And he helped to formalize the Hamiltonian system. So Hamilton's work was also mainly during the first part of the 19th century. And at the end of the 19th century, Sophus Lie started to give some modern formalism for the symmetries, dealing with symmetries. So Sophus Lie, so he wrote his most famous books around 1890, 1892, exactly. So he was Norwegian, and for instance, he formalized the concept of momentum map. And then, so Kovalevskaya was also a great expert on integrable systems. And then during the 20th century, probably Arnold is the most famous expert on symplectic geometry and Hamiltonian dynamics. So for instance, Arnold in 1964 interpreted some fluid mechanics, so Euler equation in fluid mechanics. So the dynamics of an incompressible non-viscous fluid has some geodesics on an infinite dimensional group. And this in turn, he wrote as some Hamiltonian system on some infinite dimensional space. And that helped fluid mechanics researchers to prove some stability results, mostly in dimension 2. So Arnold is the one that gave modern formalism for symplectic geometry and Hamiltonian systems. And we will see in a few minutes that Lishnerovich in 1975, and again a few years after, wrote an article where he defined, where he gave the modern definition of a Poisson bracket on a smooth manifold. So this is more or less a picture of the history of Poisson brackets and Hamiltonian systems. So there are many other people, of course, I cannot cite everyone. So we will see in a minute what these Poisson brackets are. let me give another look of the rest of the lecture. So today we deal with the first section, right? So we will see what a Poisson manifold is. This is the first line. What Hamiltonian systems are as dynamical systems on smooth manifolds. And then I will explain a bit why traditional numerical methods cannot approximate Hamiltonian dynamical systems, and why we should develop more more sophisticated numerical tools, or use more sophisticated numerical tools to construct numerical methods for Hamiltonian systems. So let us start. So this is the definition of a Poisson bracket. Everything is smooth, except if I mention the opposite. Everything will be smooth in this lecture. In particular, the manifold we work on is a smooth manifold. And then a Poisson bracket on M. Sorry. A Poisson bracket on M is a Lie bracket on the space of smooth functions on M. So a Lie bracket is a bilinear antisymmetric map from C infinity of M times C infinity of M to C infinity of M, such that the Jacobi relation is verified. So the Jacobi I just mentioned. So a Poisson bracket on M is a Lie bracket on C infinity of M, such that for all F, G, H in C infinity of M, the Leibniz rule is verified, meaning that there is some compatibility between the product of smooth functions and the bracket. Right? The product between F and G here is the pointwise product of smooth function. And the definition of a Poisson bracket has a compatibility condition between the product and the bracket. So we can make first remark. The first remark is that for all H in C infinity of M, H bracket H is equal to 0 because the bracket is antisymmetric. And this we will see later on. I don't explain why right now, that this condition, the fact that H commute with itself, the fact that the bracket of H with itself is 0, corresponds to the fact that the bracket, the energy is preserved, energy conservation. So we will see later on that smooth functions on M are sometimes called Hamiltonians, and in terms of mechanics, Hamiltonians correspond to energy. First approximation, Hamiltonian correspond to energy, and the fact that H bracket H is equal to 0 correspond to the fact that H is preserved along the Hamiltonian trajectory of H. So we will see all of this later on. So we gave two items for the definition of a Poisson bracket, two main items. First, the Jacobi relation, and second, the Leibniz rule. So let's see consequences of those 2 points. So let us start with the Leibniz rule. why do we ask this Poisson bracket to verify the Leibniz rule? Well, this is explained by this lemma. So an R bilinear map B from C infinity of M times C infinity of M to C infinity of M arises from a smooth bivector field pi by this formula if and only if B is Q-symmetric and verifies the Leibniz rule. Meaning,
Oscar.
yes.
So what is this product FG? So is it like C infinity M in reals?
Yes, it is a pointwise. It is a
Okay.
pointwise product. So this is like at the point x, it's like f of x times b gh of x. Now f of x is a number, bgh of x is another real number, and this product is one of real numbers. So this is pointwise. And as a corollary, so as a corollary, any Poisson bracket gives rise to a smooth bivector field pi. And what does it mean in coordinates? It means that if xi are coordinates on M, the coefficients of this bivector field are given by the Poisson bracket of the coordinates. This holds because we assumed M to be finite dimensional. So the right way to explain Leibniz rule is that it's a locality assumption. And if M becomes infinite dimensional, it's not so clear anymore. So Poisson manifolds of infinite dimension are much harder and probably not as well understood as finite dimensional Poisson manifolds. So everything will remain finite dimensional in this lecture. So that was for the Leibniz rule. So keep in mind that every time you have a Poisson bracket, you have a bivector field pi, and you pass from the Poisson bracket to the bivector field in coordinates using this relation that I just encircled. And sometimes we will give a Poisson bracket by giving a formula for the Poisson bracket. Sometimes we will just give the bivector or the components of the bivector in coordinates if we are on a vector space. We will pass from one language to another one without any difficulty. So that was for the Leibniz rule. How about the Jacobi relation? So propositions, Poisson brackets are particular cases of bivector fields because once we have a Poisson bracket, we get a bivector field, but not all bivector fields give rise to a Poisson bracket. And this is because of the Jacobi relation. So let me go back. If you start with any smooth bivector field pi, and you define xi bracket xj by pij, then it may happen that this bracket does not verify the Jacobi relation, right? The Jacobi identity will give constraints on the coefficient pi ij. So this is what is meant in this proposition. There is a one-to-one correspondence between Poisson brackets on M and smooth bivector fields pi, such that the map fg in C infinity of M square gives a construction of pi with df which dg satisfies the Jacobi relation. And in this case, then this is what is called f bracket g. Well, more like here. So that was the first point of the consequences of the Jacobi relation, constraints on the component of the bivector field. And a second plain consequence is what is called the Poisson theorem, meaning that the first integrals of H as a space has the structure of a Lie algebra. Or precisely, right? So we define first we take H, a smooth function on M. F is the first integral of H if H bracket F equals 0. So in this case, we say that H commutes with F. And Poisson theorem states that the Poisson bracket of two first integral is again a first integral, right? So H bracket F equals 0 means that F is the first integral of H. Same for G. And this means that F bracket G is the first integral of H again. It's an important, it's a plain consequence of the Jacobi identity. It's also a very important result because it gives a nice structure on what we will see later, that is the space of symmetries of a Hamiltonian function. So let us give some examples. We will see some examples that will follow us all along this lecture. And the first example of Poisson manifolds, probably the most important example, is the example of symplectic manifolds. So symplectic manifolds are, for us, smooth manifolds equipped with a closed two-form omega. So closed means that d omega equals 0, where d is the Durham differential, such that for all x in M, the map defined by the contraction of a tangent vector with the two form is a bijection. So this map, omega flat, is a linear map. So it is. You may assume that it is. Well, it's equivalent to say that it's a bijection or an injection or surjection, because Txm and T star xm have same dimensions. So here, Txm is the tangent space of M at small x, and T star xm is the cotangent space of M at small x. So don't mistake the big X, which is a tangent vector, with a small x, which is a base point. So we assume it is a bijection. Therefore, we can invert it. And the inverse is denoted by omega sharp. And then symplectic manifolds are an example of Poisson manifolds because one can construct a Poisson bracket on a symplectic manifold as follows. So one sees that it is linear. It is linear because omega is a two-form, and those brackets are the pairing brackets. So the Durham differential is also linear. So everything is linear in this formula. I mean, bilinear, sorry. It is antisymmetric because two forms are antisymmetric. We also see that the Leibniz rule holds because of the Durham differential in front of F and G. So this provides the Leibniz rule. The only difficulty is to get convinced that the Jacobi relation is true, and this is an averagely hard exercise. You can try. So you will make a crucial use of the fact that omega is closed to prove that this bracket is a Poisson bracket. To prove, so the Jacobi relation for this Poisson bracket is actually equivalent to the closeness of omega. That's why I wrote it here. So I told you that one may describe the Poisson bracket with the components of a bivector field. So a bivector field in coordinates is an antisymmetric, and it's a theorem which is called Darboux theorem that states that if you want to write the components of the bivector field of the Poisson bracket of a symplectic form, you can always construct coordinates such that in those coordinates the antisymmetric matrix of the bivector field is this matrix. So the coordinates in which the bivector field writes as this matrix are called Darboux coordinates. And every symplectic manifold has Darboux coordinates. So it's a strong statement about symplectic geometry. In symplectic geometry, you don't have any local invariant. All symplectic manifolds of a given dimension look the same locally because they all look like this matrix with Darboux coordinates. And then the corresponding Poisson bracket in Darboux coordinates is given by this formula. So using this formula, later on, we will recover the second law of Newton. In a way, I will tell you more precisely. So that was our first example of Poisson manifolds, symplectic manifolds, that are very important because of the fact that this map is a bijection. So the inverse omega sharp, the inverse omega sharp is also bijective. And in Poisson geometry in general, this map is no longer a bijection. It has singularities, etc. So we will see this in more detail. Sorry. Do you still see my screen?
Yeah, but it's not in the full screen mode.
Yeah. So, okay. Let's see two more examples. So, our second example is called the Lie-Poisson structure on G star. So let us pick big G, a Lie group, and Gothic G, the Lie algebra of G. Then G star, let us denote G star the dual vector space of G. Then G star comes canonically equipped with the Poisson bracket given by this formula. So let us make two comments. So this bracket here are the bracket of the Lie algebra G. And we identified G star star with G. So this is possible because we are finite dimensional. For infinite dimensional space, this isomorphism is not canonical anymore. So this is the first comment. The second comment is that you see that here in this formula, if you set x equals 0, then the bracket of f with G at 0 will vanish for any function f and g. So this is a big difference with the symplectic case. If you look again at the symplectic case, let me come back to it 1 second. Look at the Poisson bracket of the symplectic case in coordinates, for instance. You see that there's no point where the bracket of f and g vanishes for all functions f and g. So this point x tells us that this Poisson bracket has more singularities, is more singular than the one of on a symplectic manifold. Still, you may see that f bracket g at 0 is equal to 0, but this vanishes in a linear way, so kind of very gently at 0. So this 0 of the Poisson bracket is, you may say it's of order 1. Whereas on our third example, which is called cluster Poisson bracket, you see here that the Poisson bracket vanishes quadratically. Right? It is also true here that pi of 0 equals 0. The derivative of pi at 0 is also 0 because this root, if you want, is quadratic around the origin. So that provides us three examples of Poisson brackets: one that never vanishes, one that vanishes at some point at point 0 at order 1, and one that vanishes at 0 at order 2. And this will have very strong geometric consequences, as we will observe right now. If I manage to... Okay. We also need some definition of morphisms for Poisson manifolds, but this definition is very natural. The notion of Poisson morphism is exactly the same as the one of Lie algebra. So a map alpha is a Poisson map if it commutes with the Poisson bracket. So it's very natural. We will also need a notion of anti-Poisson map later on. And alpha is anti-Poisson map if it anti-commutes with the bracket. This is just a detail. And here again, let us see two examples. First example is more of a terminology, actually. Poisson automorphisms. So Poisson automorphism is a diffeomorphism, which is also a Poisson map of a Poisson manifold into itself. The Poisson automorphism of a symplectic Poisson structure is called a symplectomorphism. It's just a name. And for the linear case, linear Poisson automorphisms of the dual of Lie algebra are transpose maps of automorphisms of the Lie algebra. So my second example tells us roughly that if you remember our linear example, the canonical Poisson structure on the dual of a Lie algebra, it was made of the Lie brackets of the Lie algebra. And so it's not a big surprise that the linear Poisson automorphisms on G star are made of automorphisms of the Lie algebra. So let us see now how to construct dynamical systems, right? We want to do mechanics and dynamical systems, so we need vector fields. And this is one way to construct vector fields on a Poisson manifold. So H is a smooth function on M, as always. C infinity function on M. And we identify vector fields with derivations on M. So probably I should say derivations on C infinity of M would be more clear. Derivations of C infinity of M, more than derivations of M. And then the Hamiltonian vector field of H is said to be xh at a function f equal pi dh wedge df. So here it's relevant to notice that this is also the bracket of H and F. Denoting by these brackets, the Poisson brackets that are provided by the bivector pi. So this remark is of physical importance and relevance. Hamiltonian systems are local because the Hamiltonian vector field of H at x in M only depend on the differential dxh of H at small x and not more. So it does not depend on the value of H at the point x, and it also does not depend on higher derivatives of H. It only depends on the first derivative at the point. It's a local property. It is very important, and it captures some locality property that is very important in physics. And there is a first crucial property of the Hamiltonian flow phi th of H. So what I call the Hamiltonian flow of H is the flow of the Hamiltonian vector field of H. So phi th is the Hamiltonian flow of H at time t. And this Hamiltonian flow is a Poisson automorphism. So this provides a lot of Poisson automorphisms, if you think about it. Because once you have a smooth function, you can take this Hamiltonian vector field, integrate it, and obtain a Poisson automorphism. So this allows to construct many automorphisms of the Poisson structure. And these Hamiltonian flows are said to be inner automorphisms of pi. These automorphisms are called inner automorphisms because you constructed them using pi. You have an explicit construction to construct inner automorphisms of pi out of the Poisson bracket. So we had three examples of Poisson manifolds, if you remember. We had the symplectic manifolds, we had the Lie Poisson structure on G star, and we have this cluster Poisson bracket. So for each of these examples, we will detail now examples of Hamiltonian systems on this Poisson manifold. So the first example of a Hamiltonian system is the one of classical mechanics on M equal T star of X. So I should recall that T star of X is canonically equipped with a symplectic form and therefore canonically equipped with a Poisson bracket. So we just saw that by every symplectic structure, you can construct Poisson brackets. And now we learned that on every cotangent bundle, you can construct a symplectic form. So the intrinsic construction of this symplectic form on the T star of X is not so hard to give. Maybe I don't do it right now. I can tell you the one in coordinates. In coordinates, 2 seconds. So if you have Q coordinate on X, then once you have coordinates on a smooth manifold, you can construct cotangent coordinates on T star X, and every cotangent coordinates are Darboux coordinates for the symplectic form on T star X. Means that for the QP coordinates on T star X, if Q are any coordinates on X, QP are cotangent coordinates on T star X. And then in these coordinates, the symplectic form will be given by this matrix. And the Poisson brackets are given by the formula I gave before. So if you want an intrinsic construction of this symplectic form, you can look at what is the Liouville one form on T star X. The Liouville one form is more or less just a transpose of the differential of the cotangent projection. And then out of this Liouville one form, you can construct the canonical symplectic form on T star X. You can look at it and ask questions at the next lecture if you have some. Right, so X is a smooth manifold. In mechanics, in classical mechanics, it's called the configuration space. And then X comes equipped with a Riemannian matrix on X, which will give the kinetic energy. So the kinetic energy is this part. So more precisely, the kinetic energy is given by the square of the Riemannian metric, more precisely. And then V is a smooth function on X. V is a smooth function on the configuration space. And V is called the potential energy. And then the Hamiltonian of classical mechanics is given by the sum of the kinetic energy and the potential energy. So all the famous Hamiltonian systems you may know, like the n-body problem in celestial mechanics, for instance, but also all the Hamiltonian systems in chemistry or the one in robotics are sums of the kinetic energy and the potential energy. And this remark is a translation of what is written upstairs, but with coordinates. If you use coordinates, so Q, the coordinate on the configuration space, and P, its associate coordinate on the cotangent bundle, then the Hamiltonian system of H is given by these two equations that are, well, first order ordinary differential equation with two components. And this you can write as a second order ordinary differential equation with one component. which turns out to be actually the second law of Newton of 1687, the one that we mentioned at the beginning. So this is our first example of a Hamiltonian system. It's very important. It's the most important example of Hamiltonian system of this lecture. Because symplectic manifolds are the most important example of Poisson manifolds. Also, for some historical reasons, it's the most famous example of Hamiltonian systems. So remember, we had three examples of Poisson manifolds. The first example was a symplectic manifold. Now let us look at our second example of Poisson manifold. That was a dual of a Lie algebra. So let us look at Hamiltonian systems on the dual of a Lie algebra. So for the canonical Poisson structure on G star, the Hamiltonian system associated to H, the smooth function on M is G star here. Then the dynamics, the Hamiltonian vector field generated by H is X dot equal add star of dH at X. So let me write what is add. Add is the adjoint representation of G on itself. And here I wrote add star. So it's not the adjoint representation, it's a co-adjoint representation of G on G star. So the adjoint representation of G on itself is given by the Lie bracket of G, and the co-adjoint representation of G on G star is given by transpose of this. And here again, remember that the H, right? H is a function on G star, so dH at a point X is in the dual of G star. So this is G star star. The G star star is G again. So this is well defined. And the rest of this slide is devoted to explain an example in coordinates. So this is probably the most famous academic example of a Poisson Hamiltonian system on a Poisson manifold which is not symplectic. It's called the rigid body. So it describes the dynamics of the angular velocity of a rigid body. Meaning that under some mechanical assumption, this dynamics is the one of a body that spins on itself. So by a rigidity assumption, one can describe the dynamics of the angular velocity as living in SO3. And one ends up with this dynamical system x dot equal minus x wedge I times x, where I is the inertia tensor. The inertia tensor depends on the solid. Those are parameters of the solid. So remember that we wanted to approximate Hamiltonian systems. So at the end of the last lecture, I will show you some numerical simulations of this system. So this system is interesting because it's completely integrable. It means that there are enough symmetries to compute the trajectory. And in particular, we can prove that this trajectory is periodic. So we will see periodic trajectories of the angular velocity of the rigid body in 2 lectures. All right, so that was our second example of a Hamiltonian system in Poisson geometry. And now let us look at our third example. Our third example of a Hamiltonian system is called Lotka-Volterra. So Volterra was a biologist of the 30s, right? Approximately 1930, or maybe more like 20. That where he was modeling some population dynamics. And for this, he used, well, maybe not in his language, but in modern language, he ended up with some Hamiltonian systems for the cluster Poisson bracket. So one example of Hamiltonian system with the cluster Poisson bracket is this differential equation. And we will also provide numerical simulations of this ODE later on. So as a remark, Paul Van Eyck and his co-authors in 2016 solved this system analytically, meaning that if you do some numerical analysis to solve this differential equation, you can compare and benchmark your numerical system using these analytical solutions of Paul Van Eyck, and compare various numerical methods on this ODE. So this is also quite practical. So let us remember what the first integral is. So f, the smooth function, is the first integral of h if big F bracket big H is equal to 0. So why are first integrals so important? They're important because they provide some preserved quantities along a trajectory. So if you integrate the Hamiltonian vector field of F and the Hamiltonian vector field of H, they verify an interesting relation. meaning that they commute. But you may also integrate only one only one Hamiltonian vector field. For instance, let us integrate only the Hamiltonian vector field of H. And in this, oh, sorry, it's not 0 here. In this case, one obtains that F composed with the flow of H at any time t, so this is for all t, F composed with the flow of H at time t equal F. It means that F is a preserved quantity along the Hamiltonian flow of H. So now you can remember the first remark we made after the definition of a Poisson bracket, right? Since the Poisson bracket is antisymmetric, H is always a first integral of itself. And therefore, any Hamiltonian flow has at least one first integral, meaning the Hamiltonian itself. And in particular, if the amount of degrees of freedom is equal to 2, I mean, if you have one degree of freedom and therefore 2 dimensions, then you can integrate your Hamiltonian vector field if you know the levels of H. So this is a case for the hyperbolic pendulum, for instance. So H here goes from R2 to R. And if you try to make a picture of the levels of H, you will find the figure I plotted here. And so now you know all the trajectories of the Hamiltonian vector field of H. In particular, if H is if H of x0 is small enough, is close enough to 0, then H will remain periodic. It will draw a circle, while if H is big enough, if the energy is big enough, then you will run into infinity in infinite time. And you may notice that you have between those two regimes, you have one curve with like equilibrium here. And those intermediate regimes are called separatrix. So this is just some vocabulary, but the main point of this slide is to explain that first integrals allow to study the trajectories of Hamiltonian systems. So the first integrals are functions that commute with H. And there are stronger functions that are called Casimir, and those functions commute with any other function. So definition, C, a smooth function, is said to be a Casimir if it is the first integral for all smooth functions on M, and equivalently, its Hamiltonian vector field vanishes. So as an example, a symplectic structure has no non-trivial Casimir because remember that the map from T star M to Tm is non-degenerate. It's bijective. It means that there is no non-trivial Casimir. While for the linear case and for the quadratic case, we will remember that the Poisson bracket vanishes, and this has a counterpart in terms of Casimirs. Indeed, in the linear case, any element of the center of a Lie algebra G provides a Casimir on G star. And for the quadratic case, it's a small exercise for you to prove that if you encode the Poisson bracket in some antisymmetric matrix, then the function. So Casimirs are given by vectors in the kernel of A. Right, so let us see now maybe the most important invariant of a symplectic manifold. It's called the most important invariant of a Poisson manifold. It's called the symplectic foliation. So on a Poisson manifold M, not all the points can be connected by Hamiltonian flows, and this foliates M. So what does it mean? It means that for any H in C infinity of M, then the flow, you may at least locally integrate the flow of H and follow this trajectory. But since there are degenerate directions, right? You will not reach all the directions, and therefore it foliates the Poisson manifold. So a foliation must be thought of as a partition of M, and this foliation is called symplectic. Well, the leaves are called symplectic because on a leaf, if you restrict to a leaf, you killed all the singular directions, and therefore, a Poisson structure which has no singularity, which has no degeneracies, is symplectic. So that's why leaves are called symplectic. they have a natural symplectic structure provided by the Poisson bracket. And this foliation is singular because you may have some leaves that are close to each other, but with a very different topology. Right, so every leaf is a symplectic manifold, and the immersion of any leaf into the ambient Poisson manifold is a Poissomorphism in the sense we defined it. And the topology of the leaf of Y might differ a lot from the one of f of x, even if x and y are close. So as a remark, any Casimir must be constant on a symplectic leaf. So in general, you may look at levels of Casimir to try to describe your symplectic foliation, but it's not always true. Like we will see that, for instance, on some singular leaf, any function is constant if the singular leaf is a point, for instance. So Casimirs are not enough to characterize this leaf. Okay, so we had 3 examples of Poisson manifolds. And for every example of Poisson manifold, there is a symplectic leaf. So let us detail this. So for the symplectic Poisson structure, since symplectic Poisson brackets are not degenerate, the map from T star M to Tm is bijective, then there is no degenerate direction, and the symplectic foliation is made of one symplectic leaf. This is the whole space. Then for the Lie Poisson structure on G star, it is given by coadjoint orbits. And in particular, if you know the coadjoint orbit of SO3 star, once you identify SO3 with R3, the partition is given by spheres that are all centered at the origin, and the radius varies. So here already on this example, you see that the foliation is singular because the origin is very different. Like the leaf at the origin is just a point, whereas all the other leaves are spheres. And for the cluster Poisson bracket, you can try to compute the symplectic foliation using the remarks all along the lecture. So here I plotted the symplectic leaf of this Poisson bracket. So this is for I smaller than j, smaller or equal 3. So in general, let me emphasize that the symplectic foliation of a Poisson manifold might be complicated. So we have seen one property of Hamiltonian flows already. The fact that H is the first integral of itself. We also have seen that Hamiltonian flows are inner automorphisms of the Poisson structure. And the third important property of Hamiltonian flow is that it stays on the leaf of the symplectic foliation. So this third remark, or this third property, provides a construction of any symplectic leaf because if you are at a point, then you may try to integrate all the Hamiltonian flows and to describe a symplectic leaf that way. So now remember that we want to try to approximate Hamiltonian dynamics for a Poisson structure. So why do we want to do this? Well, first, we want to do this because for the symplectic case, it brought many results. Numerical methods that have been constructed for symplectic Hamiltonian systems have been used in many fields of mechanics, so astrophysics, molecular dynamics, optics. Here, for instance, this is a picture of what has been called the Virgo project about 20 years ago. And that project was about simulation of galaxy dynamics. So what you do is more or less, you take the n-body problem. So you simulate many planets, but here they are not planets, they are galaxies. You take many of them and you try to integrate the Hamiltonian system corresponding to this n-body problem for n big and see how galaxies evolve, like how their motion evolve. And for this, people from astrophysics used the symplectic method. So we may try to do this for Poisson system as well. So there is a recipe to construct symplectic methods. So one recipe is called symplectic Runge-Kutta. So this method depends on coefficients. So Bi, Ki, and Aij are the coefficients of the methods. S is an integer called the stage of the method. And there's a theorem that states that for some constraints on the coefficients, then the integrator is symplectic. So the question to generalize this method to Poisson structures is, could we do the same if we replace J by some pi of X? You remember that symplectic form in Darboux coordinate was constant, whereas Poisson tensors in general are not constant. So the question is, can you replace J by some phi of x here? And I proved in my thesis that this does not work, meaning that you may run into numerical issues, especially if you want to compute periodic orbits. For instance, your discrete trajectory will not be periodic at all, and in the long run, you will run far away from the trajectory. And the reason is that it destroys the foliation. So these are exercises for tomorrow. If you want, it's kind of easy exercises. And tomorrow, no, not tomorrow, next week. And next week we will see some more sophisticated mathematical tools to deal with the problem of construct numerical methods that are adapted to Hamiltonian systems for Poisson structures. So I'm done now. I'm finished for today.
Okay, thank you. So is there any question? I just have a quick one. It's about the convergence of this Runge method here. How fast is the convergence here? It's the same one that is there, or it depends on some other parameter too?
So what do you mean for this system or for that one?
Yeah. For this one.
So this one.
Yeah. Yes, this one.
So here epsilon is the time step.
Mhm.
And in that simulation, I don't know if this is your question, but in that simulation, if you take the time step, well, if you take the time step really small, you won't see this, right? It's just if you take a time step that is big enough, like if you sometimes if your computer is not powerful enough, you have to take some big time step to reach the time you want,
Mhm.
right? If you take some smaller
Yes.
time step, you have to do more iterations, and that sometimes you cannot. You don't have any time for this, for instance.
No,
Or
what
you
I'm asking is like, what are the parameters this convergence depends here? Or
as
like, is it,
the order, you mean?
yeah. What are the
So,
parameters the convergence depends?
so the order. So if you take S big, and if you choose well your coefficients, then you will have higher order in this method.
I see.
But this is normal because right, your method depends on coefficients. So the more you have coefficients, the more accurate will be your method.
Right. So the more S I will be giving, so it will have a faster rate of convergence, you mean?
If you increase the order, it will be more accurate. Yes.
Okay. Okay, thank you.
Thank you, Akash.
Okay, so then for today, let's call
So
it an end.
there is a question of Akash, I think. If a Poisson manifold admits no
Oh,
Casimir functions, is it isomorphic to some symplectic Poisson structure, or it needs to be arising out of a symplectic structure? That's a good question. If you don't have any Casimir. So one must be careful with Casimir. Is it isomorphic to some symplectic Poisson structure, or it need to be arising out of? So I'm not. So I don't understand the second part of the question. So if you have a symplectic structure, you don't have any non-trivial Casimir, but you always have some in some sense because constant functions are always Casimir, even for symplectic structures. So if you have a Poisson structure with no other Casimirs than no, that's not true. So if you have a Poisson structure with no other Casimirs than constant functions, still it may vanish at a point. For instance, if you are in dimension 2, let me write here. If you're in dimension 2, and you take f of x, so on R2, all the Poisson structures are of the form dx over dy. You see that if f vanishes at some point, for instance at 0, then this cannot comes from a symplectic structure, although this won't be enough for the arising of Casimir functions, if I'm not mistaken. So Casimir functions are, say, a sufficient condition. The existence of non-trivial Casimir functions is a sufficient condition for your Poisson structure not to be symplectic, but it's not equivalent. It's more subtle. Symplectic foliations are more subtle.
Okay, thank you so much.
Yeah.
Okay, then is there any other question? Okay, then we will meet again on next Wednesday at the same time.
Yeah.
Okay, bye. See you next week.
Yeah, see you.